We have shown that the solution to the angular part of the Schrödinger equation for the hydrogen atom gives rise to this constant. It's actually this constant up here in the numerator divided by 2mr squared. So we can write a simpler radial Schrödinger equation that now should be solved to find the eigenvalues of the Hamiltonian and the eigenvalues of the hydrogen atom by solving this, I'll say, simpler differential equation. Remember that the kinetic energy operator here is a function, if you will, of the derivatives with respect to r. And we have solved the angular part, which is now distilled here, and the potential part here is a Coulomb interaction between the electron and the proton in the atom. Now, I'm not going to go through the details of how this is solved, but it is a soluble equation. Even though it looks like a very complicated differential equation, it is one that can be solved. Unsurprisingly, what one finds is that the energy levels that result from this equation have the following form. They're equal to minus mass times energy to the fourth divided by 32 pi squared epsilon squared. Remember, that's the permittivity of the Coulomb interaction in a vacuum. H bar squared times 1 over n squared. All right, and I hope that you'll also recognize that this is essentially the same as the Bohr result. So the Bohr energies had exactly the same values. So Bohr's theory, even though not based in a good physical reality, nevertheless does a remarkable job of getting the right answer. Now, we're going to simplify, because writing this out every time is a little tedious. We're going to simplify this by making a certain definition. Okay, and we're going to define the following constant. And I'm doing this advisedly because this is not a constant that I defined, but somebody else did. If I define E sub h as not negative, but me to the fourth over 16 pi squared epsilon squared h bar squared, this in fact defines a quantity we call a hartree. And we'll learn a little bit more about who hartree was in a future lesson. But the hartree is in fact equal to 27.2 electron volts. Now, electron volts is just another way to measure the energy. And it turns out this is very handy because you can see that it's pretty much the same as this, that in fact the energy of the hydrogen atom now can be written in terms of hartrees as minus 1/2 E sub h. So if we use hartrees as our unit of measurement, then it's very easy to write the eigenvalues for the hydrogen atom in this form. And I should also mention that it's 1 over 2n squared E sub h, because we still have this n factor that goes in there. So the hartree energy is in fact something that belongs to a set of units we call atomic units. And we'll be talking about these in more detail in Module 4, but it's useful to get sort of an early picture about what these units mean. Now, I want to make some observations about these results. We've seen these results now before in reference to the Bohr model, but let's talk a little bit about what they mean. Okay, the first observation that I would make is that these energies are negative. So E sub n is less than 0. What does that mean? Well, let me draw a picture over here, and I'm going to make this a rather large picture so that we can really see the details. But when we talk about the potential between, that is, the interaction between the proton and the electron, we start and use as a reference point, so I'll write this out here. The reference is that the electron and proton are infinitely separated. That is, they're not close to one another. And that defines E equals 0. So this point here, if this is E equals 0, that's when the electron and the proton are infinitely far away. So they're way out here somewhere. All right, as they come closer together, the interaction is a negative interaction. They are attracted to one another. okay? And they're attracted as 1 over r. So the function we're going to see is a 1 over r kind of function, which looks like this. Comes down, and then it goes way down here. All right, so this is a graph of v of r, which is essentially just a negative e squared over r. And I'm going to leave out the 4 pi epsilon part of it. This is the functional part, if you will, of the Coulomb potential. Now, where do these energy levels lie? Well, the first one, when n is equal to 1, is going to be down here somewhere. So this is for n equals 1. What about n equals 2? Well, that's got to be at a higher energy, n equals 2. And in fact, n equals 2 is going to be 1/4 of energy 1. But since they're negative, that means it's 1/4. It's up here somewhere at 1/4. So this is n equals 2. n equals 3 would be 1/9 of n equals 1. So it's about a little less than 1/2 of n equals 2. So n equals 3 is up here. And I hope you can begin to see the picture that the energy levels of the hydrogen atom, in fact, get much closer. N equals 4 would be up here. And they get very close together as we go up higher and higher in energy. So in fact, what this formula is predicting is this kind of picture of the energy levels of the hydrogen atom. Okay, now I think another thing which is sort of implicit in all that we're saying here is that the energies depend only on n. They do not depend upon L. Now, why am I worried about that? Well, L is part of the Schrödinger equation that we're solving here. Why don't the energies depend upon L? Well, it turns out they don't depend on L, and in fact what they have is a degeneracy of n squared. And we're going to explore a little bit later what that means. Okay, now in case you're worried about this not depending upon L, the wave functions do depend upon L. So when we write out the radial wave functions, the eigenfunctions for this particular differential equation, they do depend on both L and n. And their dependence upon L is a parametric dependence. Okay, I've already noted that these energy levels are the same as the Bohr model, and we can also achieve the same improvement if we convert our mass of the electron to a reduced mass, which is just the reduced mass of the electron and the proton, like this. So this would also bring these energy levels into complete agreement with the experimental result. Now, one thing I'd like to note here is sometimes we learn in general chemistry about the ionization potential of different atoms. And we also talk about the electron affinity, but the ionization potential, how does that look on this particular diagram? Well, in that case, we're starting down here at the ground state of the hydrogen atom, and we're separating the proton and the electron from one another. So we're basically bringing it all the way up to 0. So the ionization potential is essentially going to be equal to the energy where n is equal to infinity. Okay, so it's the highest possible energy level minus the energy when n is equal to 1. All right, but you'll notice that this is just 0, so this is equal to negative E1, which is just 1/2 the hartree energy. And that is, in fact, the ionization energy for the hydrogen atom in this case. All right. We have also shown that these energy level results result in the right equation for the Rydberg constant, but we can say that more formally, that the energies are hc nu, and that this is going to be equal to minus 1/2 or minus 1 over 2n squared of the hartree energy. So this nu is just going to be equal to the difference in these two energy levels. So RH is the nu tilde, and that's going to be the hartree energy divided by Hc, and I should leave the 2 in there, times this. Now it'll be multiplied by this 1 over n squared minus 1 over n2 squared. So this thing here represents the Rydberg constant. All right, so once we've defined the hartree, which is a very convenient number to use, and it's useful to remember this 27.2 eV, though you can also express it in other units if you wish. But once we've defined that hartree, it makes it easier for us to define things now like the ionization potential and the Rydberg constant for the hydrogen atom. All right, next we'll take a look at the eigenfunctions for the hydrogen atom.